Section 10.2 is correlation. Correlation means basically just the relationship between two different sets of data. We're going to consider linear correlation, and there is a linear correlation coefficient R that's a number that measures how well paired sample data fit a straight line pattern when they're graphed. So let's start with the definition of correlation. A correlation exists between two variables when the values of one are somehow associated or related with the values of the other in some way. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So here's some examples of relationships between two sets of data when we do a scatter plot. So here's a positive correlation. It looks like the data values are all going up. As x gets bigger, y gets bigger. There's a positive linear correlation. This is not a very strong correlation because of all the spread. Here's an example of a negative correlation, and this is a stronger correlation here than we have here. Do you see that, how the plots tend to be tighter around some line? Look at this R value. When there's a positive correlation, R will be positive. When there's a negative correlation, R will be negative. And the closer R is to 1, the stronger the correlation is. Okay, the closer the absolute value of R is to 1, the stronger the correlation is. If this number is negative, that means that we have a negative correlation, meaning that the slope of this line would be going down. It would be negative. Here we have no correlation. If we were to fit a line through here, this would be a horizontal line, and the slope of a horizontal line is 0. Same thing happens here. If we were to try to fit a line through these points, the best fitting line would have a slope of 0. So these two examples, we would say that there's no correlation or a very, very small correlation. So the closer those R is to 1, the stronger the correlation. The closer it is to 0, the less correlation there is. Requirements for linear correlation. The sample of paired data, x, y, is a simple random sample of quantitative data. Quantitative means it's numerical. Visual examination of the scatter plot must confirm that the points approximate a straight line pattern. They don't have to be exact, it just has to be close. The outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R, both with and without the outliers included. Here's the notation we use for correlation. N is the same N that we've been using for a long time. This sigma notation denotes using a sum of the items that are indicated. So sigma x means the sum of all the x values. We saw these whenever we did the one variable statistical analysis. Also, there's a two variable statistical analysis. If you have data in two lists, you can run that. And this is the sum of the x's, the sum of the x's squared, the square of the sum of the x's, the sum of the product xy, and then R is a linear correlation coefficient for sample data, and the Greek letter rho is the linear correlation coefficient for a population. So now we have new sample statistics and population parameters. R is the sample statistic we use to approximate rho. RHO is the Greek letter here. The linear correlation coefficient, R, measures the strength of the linear relationship between the paired values in a sample. Here's two formulas we can use to calculate R, but guess what? We don't do that. What do? We love TI, don't we? Now, interpreting R, this linear correlation coefficient, there is a table in your book, and I'm not going to show you how to use the table in the book because we have the graphing calculator and we're going to use it. And it's also going to give us p-values that we can then interpret. It says if the absolute value of the computed value of R exceeds the value in table A6, conclude that there is a linear correlation. Otherwise, there is not sufficient evidence to support the conclusion of a linear correlation. We will be testing a null hypothesis here that R equals 0. If R is equal to 0, remember there's no linear correlation. If R is not equal to 0, that's just saying that there is a linear correlation. We're not saying if it's positive or negative. If we're testing the claim R is greater than 0, then we're claiming that there is a positive linear correlation. If we test the claim, the alternative hypothesis that R is less than 0, then we're looking at a negative linear correlation. Know that the methods of this section apply only to linear correlation. If you look at the scatter plot and you conclude that there's not a linear correlation, know that it's possible there might be some other association that's not linear. For example, it could be quadratic, it could be cubic, it could be exponential. Linear is not the only type of correlation there is. But in this section, we're only looking at linear correlations. Properties of the linear correlation coefficient are, first of all, R is never less than -1 or bigger than 1. It only takes on values between -1 and 1. If all values of either variable are converted to a different scale, the value of R will not change. So if we do a logarithmic transformation to our data, you don't know what that is, but it means you take the log of each number. It's not going to change the value of R, even though it changes the value of the numbers, the data. The value of R is not affected by your choice of X and Y. Switching what you call X and what you call Y is not going to change the value of R. R measures the strength of the linear relationship, and R is very sensitive to outliers, which can dramatically affect the value of R. So R is what we use to measure a linear correlation. For example, the paired shoe height data from 5 males are listed below. We can use a computer or a calculator to find the value of the correlation coefficient R. I've taken the liberty of actually plugging in this data in advance just simply because it takes so long to put data into my calculator. List 4 here represents the shoe print or the shoe size in centimeters. List 5 is the height of males measured in centimeters. So list 4 and list 5 are where my data values are. If we did a stat plot for these data, we would see this shape. And it looks like it might be somewhat linear. I can't think of anything else it might be. So we're going to assume that there's a linear pattern and there are no outliers. A few technology displays are here below. This is from Minitab, the graphing calculator, and StatDisk. These are used to calculate the values of R, and I'm going to show you how we get to this point on the TI calculator. But you see, here's the value of R. This shows a positive correlation, 0.59. Well, we have an increasing line here. We're going up as we move from left to right. So there is a positive correlation, but it's not a very strong positive correlation because 0.5 is not real close to 1. Just looking at the graph and looking at this output, we can already tell a few things about what's going on. So now the question is there a linear correlation? We found previously for the shoes in the height example that R is equal to 0.591. This is just a numerical value. So now we proceed to interpret this meaning. Our goal is to decide whether or not there appears to be a linear correlation between the shoe size and the height of people. We can use the p-value as well to interpret this. Here's a p-value for a two-tailed test. A two-tailed test means that we're looking at the null hypothesis, R is equal to 0, versus the alternative hypothesis, R is not equal to 0, and we end up with a p-value of 0.29. Typically, we compare this to an alpha level of 0.05, typically is our significance level. Alpha is still our significance level. P-value is still what we compare to alpha to decide whether or not we reject the null hypothesis or fail to reject the null hypothesis. This is a rather large p-value, 0.29. It's bigger than 0.05 anyway. So based on this p-value, would we reject or fail to reject this null hypothesis? Fail to reject the null hypothesis and conclude then that there is no linear correlation here. Or let's say it this way. There's insufficient evidence to support the claim that there's a linear correlation. There may be one, we just don't have enough evidence to show it. But we did not prove the alternative is correct based on this data. With our technology, we have a p-value of 0.294. Because that p-value is not less than the significance level of 0.05, we conclude there's not sufficient evidence to support the conclusion that there is a linear correlation. What's going on here? This is a t-statistic, by the way, that I just didn't bother to copy the test statistic here since we're using the technology and the p-values to make this decision. But with a two-tailed test, what typically happens is we have this critical region at either one of the tails. 0 is in the middle. Our R value is somewhere over here, and our critical value has to be between -1 and 1. R is always between -1 and 1. With this small sample size, there's a very narrow region here that indicates we have a linear correlation. Our test statistic did not fall anywhere as close to that region. So we conclude we fail to reject the null hypothesis. If we square the value of R, that will give us then the proportion of the variation in Y that's explained by the linear relationship between X and Y. So for example, we found previously for the shoe height that R is 0.591. If we square that, we get 0.349. 0.591 squared is 0.349. We conclude then that about 34.9% of the variation in height can be explained by the linear relationship between shoe size and height. There's other factors that come into consideration. Some common errors involving correlation. It's wrong to conclude that correlation implies causation. There's correlations between who wins the World Series and how the stock market does. But does the World Series really have anything to do with the stock market? No. So just because there's a correlation, that doesn't mean that that's implying causation. Averages. Averages tend to suppress individual variation and may inflate correlation. So you can see if you're using averages of data, you may see more correlation than what really technically is there. Also linearity. There may be some relationship between X and Y even if there's no linear correlation. So these are three things that you need to watch out for. Correlation does not imply causation, averages inflate correlation, and there's more than just linear relationships that you could have between variables. Now for the formal hypothesis test, I kind of gave you the preview of it. We have our notation. N is the number of paired sample data. R is our linear correlation coefficient for the sample. Rho is the linear correlation coefficient for a population of paired data. Our hypothesis test requirements happen to be the same as they were before for considering correlation and finding R values. Our hypothesis tests are here. The null hypothesis is rho equals 0. That means there is no linear correlation. The alternative is rho is not equal to 0, which means there is a linear correlation. The test statistic that we use here is R, and we're going to use technology to give us p-values as opposed to finding critical values. Okay, I think it's just easier to compare the p-values. So for example, we found previously for the shoes and heights example that R is equal to 0.591. Conduct a formal hypothesis test of the claim that there is a linear correlation between the two variables. Use a 0.05 significance level. What I'm going to do now is show you how to do that test on your calculator. So remember, I've already got my data for the shoe heights in the calculator in lists 4 and 5, I believe. Yes, that's right. So we're going to hit Stat, go over to Tests, and go up to the linear regression t-test. So we hit Stat, go over to Tests, and then go up to the linear regression t-test. And we hit Enter. And we end up with a window that looks like this. This is our input screen. And when we calculate, I've already got list 4 and list 5 in for my X and my Y. We're doing a two-tailed test, so alpha and beta and rho are not equal to. And we want our regression equation, so we're going to calculate. Hit Enter and scroll down because we don't yet have, well actually here we do. This is our test statistic. We're not using that. There's our p-value. This is the first screen of output that we get, and then we can scroll down and get more information. We see here that our p-value is 0.29, and based on this result, we would fail to reject the null hypothesis because the p-value is greater than alpha. This indicates that 34% of the correlation here, 34.9, can be explained because of the linear relationship between list 1 and or list 4 and list 5. Those were the lists that I used for this test. So one-tailed tests can occur. This would be a negative linear correlation. This would be a positive linear correlation, and I've already discussed that. For these one-tailed tests, the p-value method can be used like it was before. We're going to be comparing p-values to alphas. Remember, we reject the null hypothesis if the p-value is less than alpha. Otherwise, we fail to reject.